We now discuss the solution of a problem from the section Differential Equations. The problem is on the solutions of a differential equation. Not the solution, solutions of a differential equation. And this question has appeared in CSIR National Eligibility Test held on 26th November 2020, and it is from the section B. The problem is, let k be a positive integer. Consider the differential equation dy by dt is equal to y power 5k by 5k plus 2 for t greater than 0 and y at 0 is equal to 0, the initial condition. Which of the following statements is true? Option 1. It has unique solution which is continuously differentiable on the open interval 0 to infinity. Option 2. It has at most two solutions which are continuously differentiable on the open interval 0 to infinity. Option 3. It has infinitely many solutions which are continuously differentiable on 0 to infinity. Option 4. It has no continuously differentiable solution on 0 to infinity. The problem is asking you to find how many continuously differentiable solutions on 0 to 1 exist for the given initial value problem. We now discuss the solution of the given problem. We are given k is a natural number and let n is equal to 5k by 5k plus 2. Clearly 0 less than n less than 1. The given initial value problem is dy by dt is equal to y power n, where n is 5k by 5k plus 2. And t belongs to the open interval 0 to infinity, y at 0 is equal to 0, the initial condition. Call this as the initial value problem 1. Note that y of t identically equal to 0 is a solution of this above initial value problem. Y of t identically equal to 0 means y of t is equal to 0 for all t belongs to the open interval 0 to infinity is a solution for this. That is a trivial solution is also there. Now separating the variables, that means push this y power n to the other side, then it will become 1 by y power n, and 1 by y power n is y power minus n dy and is equal to dt. Integrating, we'll get integral y power minus n dy is equal to integral dt plus c, where c is the constant of integration. This implies when you integrate this, this is y power minus n plus 1 by minus n plus 1, that is y power 1 minus n by 1 minus n is equal to t plus c. Now throughout this we will be getting n 1 by n and 1 by 1 minus n, and we have already noted n lies between 0 and 1 strictly, and 0 less than 1 minus n less than 1 always, and for these values 1 by 1 minus n is greater than 1. So these are the things about n. They will be coming very often in the discussion. Now applying the initial condition, that is when t is 0, y is also 0, you apply here, you will get c is equal to 0. Then you will get a particular solution, y power 1 minus n by 1 minus n is equal to t, that is y power 1 minus n into 1 minus n into t. The solution of this given initial value problem is y is equal to 1 minus n into t whole power 1 by 1 minus n when t greater than 0, with the initial condition y at 0 is equal to 0. So that is y of t is written like this. That is the solution of the given differential equation with the given initial condition. Let's move to the next slide. Now, the solution of 1 y of t is written like this, which we have already seen. Now, define y suffix a of t for every a greater than or equal to 0 as 0 when 0 less than or equal to t less than or equal to a, and when t greater than a, 1 minus n into t minus a whole power 1 by 1 minus n. Observe that this second portion, this is 1 minus n into t minus a whole power 1 by 1 minus n when t greater than a is same as this, except that instead of t greater than 0, it is t greater than a, and 0 when 0 for t is equal to 0 in the given solution, but in this function which we are now constructing is 0 less than or equal to t less than or equal to a. So if you see carefully that this y of t, this is when you take its curve, these are called integral curves. That means the solution of that given differential equation is a curve, is a particular solution is a curve. That curve is called integral curve. So this integral curve is shifted a units to the right, So when you shift this integral curve a units to the right, then it will be 1 minus n into, in brackets, t minus a multiplied by to the power of 1 by 1 minus n when t greater than a. So that means you are shifting this curve to a units to the right, and you are dragging 0 from 0 to a. That means t will be 0 from 0 to a. So this is the situation. This is a function which you are defining. We are not saying that is the solution of the differential equation, but we are going to show it after some time. But this is a function what we have defined. Let's have a feel about this function, and let's see the graphically, and let n is equal to 5k by 5k plus 2. Let us take k is equal to 1, then n will be 5 by 7, and 1 minus n will be 2 by 7. Then the given solution y of t, is equal to 0 when t is 0, and when t greater than 0, 2 by 7 into t to the power of 7 by 2. So the integral curve is this. This is the integral curve. This is a solution. This is the solution of the differential equation. But for the function, what we have constructed here, let us shift this curve a units to the right. We are only shifting this curve. So shift that by 2 units to the right. So you are only shifting this. So 0 will remain here itself. Remain here itself. But in this function which you have defined, so when t lies between 0 and a, including 0 and a, the value is 0. So let's look at the curve of this function when a is 2. So when a is 2, y2t is defined like this. Wherever there is a, you are writing t here. And this is not the curve for this. For this portion, this is the curve. Let's see what is the curve for this. So this is up to t greater than 0, this is the curve. But when t, 0 less than or equal to t less than or equal to 2, it is 0. So let's look at it, 0 to 2, that is the straight line, what you are going to get. So that's the red one. That is the red one. That is this. So y2t is this. So y2t is this. This is, for example, 2 I have taken. But this a is greater than or equal to 0. That means a takes many values. many values. And for each a, we are getting a curve like this. So I will show you that picture in the next slide. Now, this is the initial one. You also note down when a is 0, this is yt. This is yt. And when t is shifted a units to the right, then this is the curve. This is only a shifted curve. Now, we are not saying this shifted curve is an integral curve, but we are going to show that it is an integral curve. So, this is the original one. So it is now shifted by a is a very small quantity. So, that is the curve. And next a is the next value is this. But a greater than or equal to 0, it is continuously it is taking. These gaps you won't see. So, they will be very, very, very close. In fact, very close that. And the next value of a. So, this is the one. And it goes on taking the values. So, it goes on taking the different values. So, what are you observing? For each a greater than or equal to 0, we are going to get a curve, and because a takes infinitely many values, so you will have infinitely many functions like this, and from this curve there are infinitely many. They are continuous. So, in the due course, what we are going to show is we prove the following. The first one is yat is differentiable on 0 to infinity, and ya prime t is continuous on 0 to infinity. That means it is differentiable and the derivative is continuous. Then we say yat is continuously differentiable function. And how many such functions you will get? As many as there are a. How many a's are there? Infinitely many. That means you are going to get infinitely many continuously differentiable functions. We are going to show each yat is a solution of this. So that means your initial value problem 1 is accepting infinitely many continuously differentiable solutions on the interval 0 to infinity. That is what we are going to show precisely. Let's move. This is y of t, this is yat. And now differentiate. Ya prime t is equal to differential of 0, 0. And 1 minus n to the power of 1 by 1 minus n is constant, is out. And the derivative of t to the power of 1 by 1 minus n is 1 by 1 minus n into t minus a. This is the differential, not this. This is a differential equation. T minus a to the power of 1 by 1 minus n minus 1 when t greater than a. So, when you simplify, this is 1 minus n to the power of 1 by 1 minus n minus 1. And this is t minus a to the power of 1 by 1 minus n minus 1 as it is. And you will get, this is the answer. So, this is the answer. So, this says the derivative exists. Therefore, it says yat is differentiable on 0 to infinity. Of course, we have closed here. What we want is open interval. This is clear from this. Now, so we have seen the derivative exists and yat is differentiable on 0 to infinity. Note that ya prime t is continuous on 0 to infinity. Why? Because t minus a to the power of n by 1 minus n by 1 minus n is greater than 1. So, this is this gives a continuous curve when t greater than a. And when t lies between 0 and a, including 0 and a, it is 0. So, if at all there is a discontinuity, the discontinuity will be at t is equal to a. So, let's see. Notice that when t tends to a from this side, from left, it is 0. T tends to a from right, t minus a is 0. That's precisely what you said. Limit t tends to a plus in this of ya prime t is 0, and limit t tends to a minus ya prime t from this end, that is 0. So that means the discontinuity what we have expected is not there. It is continuous there. Therefore, it is a continuous function. So ya prime t is continuous on 0 to infinity. And ya t is differentiable and its derivative is continuous. Therefore, it's a continuously differentiable function on 0 to infinity. So that is the one. So derivative, and this derivative we have seen this as 0 is 0 power n, and this you can see is a power of 1 minus n into 1 by 1 minus n t minus a to the power of 1 by 1 minus n to the power of n. So that's what it says. So now look at that. This is 0 power n. This is yat power n. And this is 0 power n. When t greater than a, this is the 1. So this is precisely yat to the power of n when t greater than or equal to 0. And ya0 is 0. So ya prime t is equal to ya t to the power of n when t greater than 0. Of course, t is greater than or equal to 0. And ya0 is 0. That means what are you seeing? So recall your differential equation. It says this yat satisfies this. So this says yat is the solution of this initial value problem for every a greater than or equal to 0. And yat is not only a solution, it is continuously differentiable on 0 to infinity. How many such continuously differentiable solutions are there? Since a can be chosen infinitely many ways, the initial value problem has infinitely many continuous differentiable solutions on 0 to infinity. Let's look at the options. In the options, option 3 says it has infinitely many solutions which are continuously differentiable on 0 to infinity. Therefore, our answer is the option 3 is true. So that is the discussion of the solution of the problem from the section differential equations, and we are discussing the continuously differentiable solutions on the open interval 0 to infinity for a given initial value problem. I hope that you have understood the solution of the problem, and I wish you all the best. Thank you.